Hello. This is going to be the start of a video on section 7.4 on trigonometric substitution. I'm going to break this into multiple videos just because I'm kind of writing this piece by piece and I don't want to have to commit to talking all in a row. So I will get through some of this and then finish it in one or two other videos. Just one thing worth mentioning, it'll show up in this section. I may have alluded to this elsewhere, but I don't think it's formally in the notes anywhere else. The identity for sine of a double angle is 2 sine theta cosine theta. So be ready to use that. You don't necessarily have to have it memorized. So let's jump into a motivating example. Suppose we had this definite integral. Integral from 0 to 4 of the square root of 16 minus x squared. So if we draw a picture here, my hope is you know that that is a semicircle centered at the origin with a radius of 4. So if we interpret this as an area, right, we actually know the answer. It's 1/4 of the area of the entire circle. So it would be 1/4 of pi r squared. R is equal to 4. So it's 1/4 of pi times 4 squared. And so we know the answer is 4 pi. But could we actually get that by doing fundamental theorem of calculus? Do we know how to actually find an antiderivative for that thing? We don't, not right now. But we are going to figure out a way of harnessing what we already know to do that integral and others that are similar to it. So we want to somehow make this simplify, right? We have the square root of 16 minus x squared. And certainly what I hope no one does is say, oh yeah, it simplifies like that, it's 4 minus x. That is not a valid rule. But we do want to create some kind of way of taking this thing and making it easier to deal with. So what you want to start doing, and this probably wouldn't be obvious to you, but we want to be on the lookout for things in our integral that remind us of things that we see in trigonometric identities. So here's an example of a trigonometric identity. 1 minus sine squared equals cosine squared. And I'm actually going to write this as 1 squared to illustrate a point. The pattern here is I have a number squared minus some variable expression squared. That's the kind of pattern we're seeing. Here, again, let's think of this as 1 squared. Here we have number squared plus variable expression squared. That's something we see in a trig identity. And then here's the same one, but backwards. Here the pattern is variable expression squared minus number squared. All of those can simplify if applied to certain trig functions. If we're talking about secant, something like this simplifies. If we're talking about tangent, something like this simplifies. If we're talking about sine, something like this simplifies. So we want to create some sort of substitution so that this thing under the radical turns into something that simplifies. And if it turns into a perfect square, all the better, because we're taking its square root. So we're going to make what's called a trigonometric substitution. So I'm going to say, what if x is equal to 4 sine theta? So maybe it's not obvious where that came from, but you'll see how that's convenient. So for now, I'm going to forget about the limits of integration and do the corresponding indefinite integral. Because we already know the answer to the definite integral, we really want to think what's going on from an anti-differentiation point of view. So I'm going to make this substitution. So I have x is equal to 4 sine theta, which would mean dx over d theta is 4 cosine theta, which means dx is 4 cosine theta d theta. So with that in mind, let me substitute. I have the integral of the square root of 16 minus, well, x squared would now be 16 times sine squared. and dx is now 4 cosine theta d theta. So I've made my substitution, and let's see what happens. This thing under the radical is just 16 times this pattern with 1 minus sine squared, right? So it's not literally 1 minus sine squared. It's 16 copies of 1 minus 16 copies of sine squared, which would be 16 copies of cosine squared. And now we'll take a square root, and I will just tell you, we're going to assume that everything we're dealing with in these problems is positive. So don't worry about, oh, I'm taking the square root of cosine squared. What if cosine was negative? Just assume everything is positive. So here we have 4 times cosine theta, and here we have 4 times cosine theta. So we're integrating 16 cosine squared theta d theta. Right? And here's the good news. We know this, right? Maybe we don't have it memorized, but we've recently seen that this is possible. This is something we can integrate. So what we're going to get here as our antiderivative is 16 times, our antiderivative for that was 1/2 theta plus 1/4 of sine of 2 theta. Right, and there's a plus c at the end. So when we work out all of that, it's 8 theta plus 4 sine 2 theta plus c. Now, we've done our antiderivative, but we're still trying to answer the question. So I'm going to do 2 different things from here. If we were just concerned with doing this specific definite integral problem, we could change the limits of integration. So we said x is equal to 4 sine theta. So if x is equal to 4, that means 4 equals 4 sine theta. Sine theta equals 1. And for problems in this realm, we're always going to make the most natural assumptions in terms of being in the first quadrant whenever we think that's plausible. So theta would be pi over 2. If x is equal to 0, we would have 0 equals 4 sine theta, which means sine theta is equal to 0, which means theta is equal to 0. So if we wanted to, we could actually rewrite those endpoints. So I'm going to quickly get the numerical answer. So if we were trying to, and you'll notice I knew this would take a lot of room. So if we're just trying to do the definite integral, we have our antiderivative. And we want to evaluate from x equals 0 to x equals 4. And we just saw that that was the equivalent of evaluating that as theta goes from 0 to pi over 2. So if we plug in pi over 2, we have 8 times pi over 2 plus 4 times pi, sine pi, sorry. If we plug in 0, we have 0 plus 4 times sine 0. So this is 0, this is 0, this is 0. Our answer is 8 times pi over 2, which is 4 pi, which we already knew from geometry, but here we're seeing how we can actually get to it from the calculus. But what might be more interesting is actually figuring out what is the general antiderivative. Right, so let's continue with the indefinite integral, because that's interesting. Right? We've answered the question, but what if it wasn't a definite integral? What if I was asking you for an indefinite integral? So here we have to substitute back. And this is more complicated than when we substituted back with U substitution. So let's remember, what we know here was that x was equal to 4 sine theta. And it's not like we see x here. We can't just plug in. We have to reverse this. So one thing I could do is I could say x over 4 is equal to sine theta. So again, assuming that we're in a nice quadrant, theta would be inverse sine of x over 4. So that's how we could rewrite this thing. But we also have to rewrite sine of 2 theta. So I'm just doing some kind of scratch work here. Here is where I'm going to use that identity from before. So sine of 2 theta. I'm doing this kind of small because it's not really with the main thrust of my problem. Let's actually separate this. And we'll continue with our indefinite integral over here after we've done some work. So sine of 2 theta is 2 sine theta cos theta. Well, I know that sine theta is x over 4. So this is 2 times x over 4 times cosine theta. In order to substitute in cosine theta, we really need to use how sine and cosine are related. You can do this with an identity, but in some cases, you're not going to have the right identity at your fingertips. What I would recommend is let's just draw a little picture to illustrate this relationship. Let's assume everything is positive, and we're just going to draw a little right triangle to illustrate that sine of theta is equal to x over 4. So if theta is here, sine is opposite over hypotenuse. So we could illustrate that like this. If I have a triangle that looks like this, then sine of theta is x over 4. By the Pythagorean theorem, this third side would be the square root of 16 minus x squared, which has been lurking in the problem. That was what we started with. We saw 16 minus x squared in the very beginning of the problem. So based upon this picture, we could say cosine of theta is adjacent over hypotenuse, which is root 16 minus x squared over 4. And all of this simplifies to x times 16 times square root of 16 minus x squared over 8 after I simplify. So if I continue with the indefinite integral, here is what the antiderivative was in terms of theta. So in terms of x, I would have, well, it's 8 times theta, and theta is inverse sine of x over 4, plus 4 times sine of 2 theta, and sine of 2 theta is this expression here. X times root 16 minus x squared over 8. So when we simplify that, we would have 8. There's a plus c all along. We would 8 times inverse sine of x over 4 plus x square root of 16 minus x squared over 2 plus c. Right? And this feels kind of bonkers. Right? We started with something that didn't look terrible. Right? This is not super duper complicated, but its antiderivative is quite complicated. And this is something that we notice. Sometimes, yes, we can do integrals, but when radicals or trig are involved, we get really weird answers, even when we can do them. Since we've come this far, let's check it. And I'm going to put this in the video. I don't know if I will do it in class, but let's actually try to check this thing. So let me separate this off. This is all just kind of my scratch work. So I want to check. So if y were equal to this whole thing, what would y prime be? So y prime would be 8 times the derivative of inverse sine of x over 4. So that would be 1 over the square root of 1 minus x over 4 squared. That's just our inverse sine pattern. Times, by the chain rule, 1/4, because that's the derivative of x over 4. For the rest of it, I'm actually going to move this because I think I'm going to need a ton of room. Oops. Oh, did I lose that? There we go. For the rest of it, I'm going to just factor out a 1/2 and do product rule on these two things. So that would be derivative of the first, which is 1, times the second, which is just radical 16 minus x squared, plus the first times the derivative of the second. So that would be 1/2 times 16 minus x squared to the negative 1/2 times 2x, negative 2x from the inside. So let's just clean all of this up and see if somehow when we simplify, we get what we're hoping to get. So here I would have 8 over 4 is 2. And I'm going to actually try to clean this up. So I have 1 minus x squared over 16. And while I'm here, I'm going to write 1 as 16 over 16. And I'm just going to combine these. So rather than write these in all different steps, I'm kind of doing it all at once. Okay, there's more simplification to be done, but we'll leave that for now. Now here, if we distribute 1/2 there, we just get 1/2 times radical 16 minus x squared. And then here, let's see, the 2 cancels with the 1/2. I would have negative x squared over radical 16 minus x squared. Negative 1/2 power means the radical's in the denominator. The rest of that simplifies to negative x squared. I'm actually going to add a page. This is just a total nightmare to check, right? This is one where maybe we just want to trust that it works. It's also the kind of thing where someone else has done a lot of these tricks and maybe you could just look it up in the first place. But we will continue to simplify. So here, I am going to notice that I have 1 over the square root of a fraction. So that's actually the same as the square root of the reciprocal. And I'll just continue like so. Now I'll break this up. It's the square root of 16, which is 4, over the square root of 16 minus x squared. And 2 times 4 is 8, so I'll just adjust that here. So I have 3 different expressions. And I'm going to create a common denominator. So here I have 8 over 16 minus x squared. Actually, let's make my common denominator 2 times that, because I actually have a fraction. So, sorry about that. We'll make this 16 over 2. 8 is 16 over 2 with this in the radical. Now this one already has the 2 in the radical, so we'll multiply top and bottom by radical 16 minus x squared. But radical 16 minus x squared times radical 16 minus x squared is 16 minus x squared. And then here we'll multiply top and bottom by 2. Something has gone wrong here. Let me see if I can find my mistake. This is what happens when I do it without looking at my notes. If you're watching this video, just be patient with me. Let me see if I can find my mistake. Maybe I can cut this out. Oh, here's the issue. Okay, so sorry about that. Okay, I forgot to distribute this 1/2 over here. So this 2 and 1/2 cancel, but they're still getting multiplied by the 1/2 over here. My apologies. I knew something wasn't going to cancel. So that should be a 1/2. There should be a 1/2 here. There should be a 1/2 here. And then there's no 2 there. We already have that 2 in the denominator. So when we combine all of our like terms, we get 32 minus 2x squared over 2 times 16 minus x squared. Dividing by 2, we have 16 minus x squared over square root of 16 minus x squared. And that simplifies to 16 minus x squared. So we got there. Let's just recap. No one said this is easy. No one said this was fun. No one said this is simple, but it's doable. In this particular case, we noticed that this pattern of something squared minus something squared kind of reminded us of this trig identity. So we made a substitution to make that happen. And then we just followed all the way through. And then we substituted back in this very clever way. And then even checking was a nightmare. But we have found our antiderivative. We solved the definite integral problem much more easily. And we found our definite integral eventually. So just a couple of comments here. What you see in your integrand should motivate the kind of substitution you want to try. So if you see, for example, a squared minus u squared, we'll try what we did here. Because what will happen is we will have a squared minus a squared sine squared, which simplifies to a squared cosine squared. Right? So that's one term instead of 2. If there's a radical in there, even better. If we see that we're adding them together, we'll try tangent. Because there we would have a squared tangent squared theta plus a squared, which simplifies to a squared secant squared theta. And if we're subtracting in the other order where it's variable minus number, then we'll try secant. So then it would be a squared secant squared theta minus a squared, which simplifies to a squared tangent squared theta. Okay, so keep those in mind. What we want to emphasize here is the kind of substitution we made is actually very different from U substitution. So in U substitution, I'll just kind of put an example up here. Right? We might have something like, oh, I'm doing the integral of 3x plus 1 to the 6th. And we would say, oh, I see that this whole expression is getting raised to the 6th power, so I'm going to introduce my new variable, u, to stand for this thing that I already see in the integral. So the new variable is all by itself, standing for something we see. In trigonometric substitution, that's not true. In trigonometric substitution, the new variable that comes into play is theta, so we can talk about trig. But that's not all by itself. We're going to make substitutions like x equals 4 tangent theta. The new variable is hidden within this expression, and the old variable is by itself. So it's a different way of doing substitutions. As with other techniques like U substitution or integration by parts, this is something we can try, but there's no guarantee it'll work out. Maybe things will not cancel in a way that is helpful. Maybe we will not get a trigonometric integral that we know. And even if it does work out, as we saw in this very first example, it's complicated. But it's possible, right? And it motivates a lot of what's in tables that people will eventually look up. And one thing I want to emphasize again is if we're going to switch back to our original variable, we will need to make sense of various trig expressions. So I highly recommend just assume we're in the first quadrant. In applications, we would be. Assume we're in the first quadrant and just draw a right triangle to represent your original substitution. So for example, this one that I had here, suppose that if we had the substitution x equals 4 tangent theta, that means tangent theta is x over 4. And I can just draw a little SOHCAHTOA diagram to illustrate that. So here's my theta. Tangent is opposite over adjacent. So just this picture here illustrates tangent of theta is x over 4. By the Pythagorean theorem, this would be the square root of x squared plus 16. And so maybe after doing all my trig substitutions, later on I realize I need to know secant theta. Well, I can use that diagram. Secant theta is 1 over cosine theta. Cosine theta is adjacent over hypotenuse, so this is basically hypotenuse over adjacent. So if I needed secant theta to make my substitution, secant theta would be the same as root x squared plus 16, which is our hypotenuse, over 4, which is the adjacent. If I needed to know sine theta, it's x over square root of x squared plus 16. Just draw the picture, right? Don't try to do it in your head. You don't even use identities because maybe you're going to mess something up. I highly recommend drawing the picture to illustrate what substitution have I made. How can I visualize that so that I can figure out the other trig functions? Okay, I'm going to stop for now. This has already been quite long, and there's more that will come in another video.